Electron configuration describes the way in which electrons are arranged in orbitals around the nucleus. Electron configurations give us insight into an element's properties and chemical behavior.
It's important to know what orbitals are in order to determine electron configuration. An atomic orbital or electron cloud is a region with a high probability of finding an electron with a particular amount of energy. There are three principles that can help us understand an electron's configuration and give us insight into an element's properties and chemical behavior. The alpha principle says that electrons will occupy the lowest energy orbitals first. The Pauli exclusion principle says that no more than 2 electrons can occupy an orbital, and if 2 electrons are to be in the same orbital, they must have opposite spins. Hund's rule says that when filling orbitals of the same energy, each orbital in the group will half-fill first, receiving 1 electron, before any will double up. When writing an element's electron configuration, the large number on the left is the principal energy level. The letter S, P, D, or F indicates the sublevel. The S sublevel has 1 orbital, the P sublevel has 3, the D sublevel has 5, and the S sublevel has 7. Each orbital can hold 2 electrons. The superscript number is the number of electrons in that sublevel.
To understand electron configuration, we can think of it as determining an electron's address. Think of each principal energy level as a neighborhood, each sublevel as a street, each house as an orbital, and each floor as a spin. Now, electrons like their space, and they also like saving money, so they start moving into the cheapest neighborhoods first. As they move into each house, each electron will start to move into the first floor of each house because Hund's rule says electrons don't like each other that much, they only tolerate each other. So when you fill them up, first floor of each house first, then they start doubling up. Now, a funny thing happens when we get to D streets. D street houses are more expensive, so it becomes cheaper to move into the S street of the next neighborhood before going back to move into the D street. Now, F streets are even nicer, so it doesn't become cheaper to move into an S street until the next 2 S streets have been filled. Now, we go back to 4F. And we could potentially just keep going.
Now here's a song to help you remember the order of the electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10.
An element's properties, reactions, and compounds are strongly related to their electron configurations, especially their outer electron configurations. Valence electrons are the electrons in the outermost principal energy level. Every element is looking to have 8. This is called the octet rule. This doesn't apply, however, to hydrogen, which looks to have 2 valence electrons, and boron, which looks to have 4 valence electrons. This is why ions will have the same electron configuration as a noble gas.
So now we're going to talk about when elements will form ions to try and gain noble gas electron configurations. So first I'm going to show you the electron configuration for sodium, which is Na. And that's so as you can tell, it's a pretty simple electron configuration. And now I'm going to show you the electron configuration for neon, which is marked as Ne. So if you compare the 2 electron configurations, you notice there's really only one significant difference, and that's this 3s1 part. So what sodium will do is it will give up its electron in its valence shell, which is the 3s1 electron, to form a sodium ion, which is marked as Na+. And this electron configuration would be, which is, as you can tell, the same electron configuration as neon.
It's important to understand valence electrons because valence electrons are what cause bonding. Ionic bonding is a transfer of electrons. Non-polar covalent bonds are when electrons are shared equally, and polar covalent bonds are when electrons are shared unequally.
If you look at your periodic table, you can actually see a number of patterns that help you remember a lot of properties of an element. Atomic radius decreases as we go up and across our periodic table, which makes francium, which is in this corner, have the largest atomic radius. It decreases as we go up because we have fewer principal energy levels. Elements are smaller as we go across because of the nuclear charge or strength of attraction the protons have on the electrons, which gets stronger as we add protons. But why doesn't nuclear charge increase as we go down? We're still adding electrons, right? That's because of the shielding effect, where innermost electrons block valence electrons from the pole of the positively charged nucleus. The more principal energy levels, the more layers of inner electrons available to shield the valence electrons. Ionization energy, or the energy required to remove an electron, and electronegativity, or an element's ability to attract an electron, increase as we go up and across the periodic table. The ionization energy increases as we go up and across because the effective nuclear charge is increasing, making it harder to remove an electron. But that's also making it easier for the element to attract electrons, causing electronegativity to increase. So as you can see, the periodic table can show us a lot of interesting patterns, even patterns for electron configuration. Groups 1 and 2, so these two, are the s block. Groups 13 to 18 are the p block. Groups 3 to 12, or the transition metals, are the D block. Then the lanthanides and actinides, which are on the bottom of the periodic table and happen right here, are known as the F block. So, using this, we can follow a pattern to find the electron configuration for a certain element. Now we're going to use the periodic table to do the electron configuration of 3 different elements to give you an idea of how it works. So the first one we chose to show you is magnesium because it's fairly simple as it doesn't have any D or F block parts to it. So what you're going to do is look at your periodic table and you see that the 1s sublevel is filled. So you're going to do 1s2. And then you see that the 2s sublevel is filled. So you do 2s2. And then that the 2p sublevel is filled, so 2p6. And then you see that magnesium is at the end of the 3s2 block. So you're going to write a full 3s2. And that would be the electron configuration for magnesium. Now we're going to show you the electron configuration for bromine, which is a little more complicated as it has some D sublevels. So it has the 1s2 filled, the 2s2, the 2p6, 3s2, 3p6. And then this is where you'd want to write 3d10, but that would be incorrect. Because look at the periodic table, 4s2 comes before 3d10. So you're going to write 4s2 and then 3d10. And then if you look, bromine is in the 4p sublevel, and it's the 5th element in, so you write 4p5. Now we're going to show you mercury, which is even more complicated than bromine because it does have an F sublevel, but don't worry, after watching this you'll understand how it works. So the 1s2 is filled, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, and then this is where our F block comes in. If you look, the F block comes before the D block, and it's going to be 4F14. And then mercury is the last element in this D block, so you're going to end at 5D10.
Another way we can show an electron's location is through an orbital diagram. Remember, the Pauli exclusion principle says that electrons in the same orbital must have opposite spins. Orbital diagrams use circles or boxes to show orbitals. Use up or down arrows to indicate electrons of different spins.
We're going to show you an example of an orbital diagram using phosphorus, which is in the 3p sublevel on the periodic table. Now each line that I draw is representing a different orbital in each sublevel. So, as you know, in the 1s sublevel, there's only 2 electrons. So there's only going to be 2 electrons in each orbital. The Pauli exclusion principle will tell us that each electron will spin in a different way. And this is represented by an up arrow and a down arrow. And so, since it's in the 3p, we know that the 1s is filled. And then we would fill up the 2s. And then we move on to the 2p. And since there's 6 electrons, there's 3 orbitals in the sublevel. And Hund's rule tells us that we would fill up, we would half fill the orbitals before we would start pairing them up. So even though it's completely filled, you want to draw your up arrows first. And then we get to the 3p. And on the periodic table, phosphorus is only going to have 3 electrons because of where it's placed. So you're only going to have up arrows in this situation. And that would be the orbital diagram for phosphorus.
We can shorten an element with a long electron configuration by using an abbreviated configuration, or noble gas configuration. To write a noble gas configuration, go up 1 row and all the way to the right to the noble gases. Write the noble gases symbol in square brackets, then write the rest of the configuration from that point.
So we're going to show you an example of when it would be a good idea to use a noble gas electron configuration. We chose palladium because it's farther down on the periodic table. It's in the 5th period, and it's kind of annoying to write out an entire electron configuration for that far down the table, especially element 46. So what you're going to do is find the noble gas and the period above it. And in this example, it's krypton. So you're going to write So that's what you do with the noble gas. And then continue to go on with your electron configuration from here. So 5s2, 4d, and that would be the noble gas electron configuration of palladium.